Hello everybody, in this video we will be going over a work done by friction and work done by gravity physics 1 example problem featuring this man and his crate. So let's get right into it. A 250 kilogram crate slides 5.2 meters down a 28-degree incline and is kept from accelerating by a man who is pushing back on it parallel to the incline. The effective coefficient of kinetic friction between the crate and the surface is 0.40. Calculate the work done by friction and the work done by gravity. So because this is a work problem, the work equation is work equals force times distance. We know there are going to be distances and forces present in this equation. So the best thing to find the forces and to just evaluate the whole system here is to draw a free body diagram. So let's do that. So before you become overwhelmed with all these forces, we're going to explain where each one's coming from and why it's pointing in the direction that it is. And then we're finally going to go over which ones we're actually going to need to solve this problem. So first to the bottom we have mg. This is weight or mass times gravity. This is always pointing straight down for every object on Earth. That's where gravity is pulling it. Therefore it's always going to be straight down. And this right here is a mass. This is an acceleration. They come together and equal a force. In this case it's in newtons. And that's the same with all of these right here. So then up here we have the force due to friction. This is pointing in the upwards direction, and it's also pointing parallel to the surface that our object's lying on. So here's the surface, and here's the force's direction, parallel to the surface. That is always true with friction, always parallel to the surface. And then it's pointing upwards because friction opposes the direction of motion. So because gravity, essentially, the weight of this crate is pulling it downwards, remember it moved 5.2 meters down, therefore friction is going to want to keep it in place. So it's going to pull the crate upwards, or at least suspend it upwards. And then we have the force due to push, and this is derived from our statement here. A man is pushing back on it parallel to the incline. We can see that there. That's where that comes from, and it's in the same line of action as the force due to friction because he is pushing from this side, and that force translates through out to the other side. Up here we have the normal force, and by definition this is perpendicular to the surface in which the object lies on, always perpendicular, and it's equal and opposite to the that object's equivalent weight on the other side. So in this case it's going to be mg cosine of theta, not mg. It's always equal and opposite to the weight pointing outward from the surface in which the object lies on. So it's not mg, it's mg cosine of theta. So finally we need to explain where mg sine of theta, mg cosine of theta, and this angle are actually coming from. So if we take a look here, this is basically, this is our restatement. Let's just pretend this is our restatement. So here's a 28-degree angle on the bottom here, right? That was specified right up here, 28-degree incline. Here's our box like it was before. And if we could just make a right angle triangle with the mg force of this crate, so this is going right down through, translating through, we can make a right angle triangle, right? So here's our right angle, 90 degrees. That gives us 62 up here. And then if we bring that over to a 90, then we can complete it by adding 62 and 28. So now we can find this force here, which translates right through, which will give us our normal force by taking mg. So this is our mg, right? This is going to be mg cosine of theta, because essentially because this angle is between our resultant force here and our y component, we'll call this our y-axis now and our x, because it's between our resultant force and our y, we're going to use cosine. And then over here, because our angle is not touching the x component, we're going to use sine. So that's a very easy way to remember it. The side that the angle is touching is going to be cosine. The side it isn't touching is going to be sine. So now that we know all of our force directions and where they're coming from, we're going to actually solve for work. So work done by friction equals force times distance. And we're going to start with this fairly simple equation and just keep breaking it down into smaller and smaller components until we know all of the coefficients within the equation. So let's start doing that right now. Do we have the force of friction in that direction? Okay, so no, we do not. This is our force due to friction, and it's an unknown. We have no idea what it is. Once again, for work done by friction, we want to find the force times distance in this direction. So here's our force, and here's our distance. We want to find them both in the same direction. They're going to be along this line of axis. So we don't have the force, but we do have the distance. It's actually given to us. If you recall, this side of the triangle was actually given to us as 5.2 meters. So we know that. So distance is not an unknown, but force remains an unknown. But if you remember, the force done by friction equals mu k. So the coefficient of kinetic friction in this case, because it's moving, multiplied by the normal force. If this was motionless, it'd be in static friction, so it'd be mu s. So we can go ahead and actually just plug that right in our work equation. So work done by friction equals mu k, and yes, I'm saying mu, that's what it's called, times the normal force times the distance. So we know mu, we know the distance. However, we do not know the normal force, except because we solved mg cosine of theta and proved that it's true, that it actually is equal to the normal force. We can just substitute that in for the normal force and see where that gets us. So now we have work done by friction equals mu k multiplied by the mass multiplied by gravity multiplied by cosine of theta multiplied by distance. So we have mu k, we have mass, that's up here. Gravity is assumed to be 9.81. We have our angle, we designed it so it would be 28 degrees. And then we have our distance, which lies on this axis, and it was given in the problem statement. So this right here is our force. This right here is our distance, and we are ready to plug in and solve. So plugging in and solving, we have to do one minor adjustment real quick. Basically, this is going to be a negative, because if you recall, our force due to friction is pointing upwards, right? That's the force of friction, while our crate is moving in the opposite direction. Therefore, it's essentially making negative work. It's making negative progress because friction's pushing up and the crate's going down. Friction is not winning the battle. It's a losing battle for friction. Therefore, it's going to be a negative, moving in the opposite direction. So our coefficient multiplied by mass multiplied by our acceleration, we're assuming 9.81 meters per second squared, and multiplied by the cosine of the angle multiplied by the distance. So plug that in to your calculator device thingy, and we get negative 4,504 joules. And once again, a joule, just to prove that it is in joules, we have a kilogram here multiplied by a meter per second squared multiplied by a meter. Okay, I'm getting that from this, this, and this. The rest are unit list. Therefore, you multiply those together and you get a kilogram meters squared over second squared, and that simplified, because we like to simplify units in science, is a joule. So that's in joules. And then we have to do one more thing before we get our final answer, and that's sig figs. In our problem here, you can see we were given 2 sig figs in every single variable, so it's going to be 4,500 joules even, and that's a negative. So that's our work done by friction. Moving on, we're going to do the exact same thing for the work done by gravity. So work done by gravity is force times distance. And like friction was the force in this direction and the distance in this direction, gravity is always the force in the vertical direction and the distance in the vertical direction, while friction is always parallel to the surface of the object. So, do we have the force? We most certainly do. We have mg right here, mass times an acceleration. So we can plug that right in. So work done by gravity is mass times gravity times the distance traveled. However, we do not have the vertical distance, but we can solve for it fairly easily with an old thing we learned in high school here. So let me write down the restatement again. So that's 28 degrees there, 5.2 meters here, and we want to find the vertical distance it traveled. So if you remember SOHCAHTOA, we can use this in this scenario, and I'm just going to skip right to the conclusion. You can go through any one you want if you don't know how to do it already. But basically, we're going to need sine, and it's going to equal opposite over hypotenuse. So, because we know hypotenuse, in this case it's 5.2, we can rearrange this equation, multiply by the hypotenuse on both sides. Okay, so let's go ahead and do that. So then we have hypotenuse sine, and this is the angle, by the way, so this is going to be sine of the angle equals the opposite side. And that's exactly what we're looking for. So we can go ahead and plug that right into our D right now. So work done by gravity equals mass times gravity times the distance, which is D essentially, because we're labeling 5.2 as D, and that's going to be multiplied by the sine, of the angle. So this is our force, this is our distance, and we are ready to solve. Once again, vertical force, vertical distance. We solve for this side of the triangle, which provides for us the vertical distance. So now plugging in, we have work done by gravity. And in this case, it's positive because, once again, our crate is making downward progress, and the positive direction we are assigning for gravity is in the downward direction. So therefore, this is going to be positive overall. Even if you assign both these as negative, it would still come out as positive because these are multiplying each other. So the mass, 250 kilograms, multiplied by the acceleration, 9.81 meters per second squared, multiplied by the distance, so 5.2 meters, multiplied by the sine of the angle, so sine of 28 degrees. Plug that in your calculator. This time we're going to get positive, remember. It's going to be 5,987 joules, and I proved to you why it's in joules. And once again, like if you remember from work done by friction, we're going to want to get sig figs here, and you might notice we can't actually round to 2 sig figs because it just won't work, because the 9 has to round up as well. So therefore we have to round to 1, because 3 would be we don't have 3 sig figs hardly anywhere here, so that's not even realistic. That would be in degree of accuracy we can't really justify. So that's going to be 6,000 joules, 1 sig fig, positive, and we are done. I really hope this helped you guys, and thank you so much for watching.